Okay, let's prove that there are an infinite number of prime numbers. So the proof is going to be by contradiction. Let's suppose, for the sake of argument, that there are a finite number of prime numbers. If there's a finite number of prime numbers, then there's got to be a largest one. So let capital P be the largest prime number. Let's define a new number, capital N, is equal to P factorial plus 1. Okay, then there are two cases. So case 1. Case 1, n is prime. Well, if n is prime, n is also bigger than p because it's p factorial plus 1. So that can't happen because n is bigger than the largest prime, capital P. So that can't happen. Case 2. Well, if n is not prime, then n must be composite. Well, if n is composite, then n has a prime factor q. If it's a composite number, then there's got to be some prime number that is a divisor. But this is a problem because n is equal to 1 times 2 times 3 times 4 times 5 all the way to n. That's n factorial, pardon me. Okay, so since q is prime, and p is the sorry, I wrote this down incorrectly. I wanted this to be p, not n here. Write that down again. P factorial is equal to 1 times 2 times 3 times 4 times 5 all the way up to p. Since q is prime and p is the largest prime number, that means that q is less than or equal to p. In other words, q must appear in this list of factors here. So q must be a factor of p factorial. Q is less than or equal to p. That means q must appear somewhere in this list of numbers from 1 to p. And so when I multiply them together, q must be a factor of p factorial. Also, q does not divide 1. Because q is a prime number, it's not going to be a factor of 1. So because q is a factor of p factorial, but it is not a factor of 1, that implies that q is not a factor of p factorial plus 1, or q does not divide n. And that's a contradiction because q is supposed to be a factor of n. And so we conclude that there are infinitely many prime numbers. there are infinitely many prime numbers. And that ends the proof.